Welcome back to the deep dive. So we talk a lot on this show about technology moving fast,
Hmm.
and we usually reference Moore's law, that golden rule of computing where processing power doubles every 18 months or so.
Right. The rhythm of progress for the last 50 years.
Exactly. But looking at the research for today's deep dive, it seems we've finally hit a wall. Or maybe it's more accurate to say we've hit a flood.
Yeah, definitely less of a wall and more of a tipping point. I mean, we've entered an era where the sheer amount of data we generate is actually outpacing the physics of how we store and process it.
Wow.
It's with the source material, this massive survey from the Journal of Information Sciences we're looking at today calls it the data deluge.
The data deluge. And that is the absolute focus for today. We aren't just talking about, having a lot of files on your hard drive.
No, no, no,
We're
no.
looking at a fundamental shift in how science and business work. The researchers actually call it the fourth paradigm of scientific discovery.
Right. And to be clear to anyone listening, this isn't just a marketing buzzword. It's a structural change in how human beings acquire knowledge. To really get the fourth paradigm, you have to briefly look at the first three.
Okay, let's walk through that evolution
Yeah.
because I think most people still think science works the way it did in their high school chemistry class.
Exactly.
Yeah.
So thousands of years ago, you had the first paradigm, empirical science.
Right.
This is purely observational. You look at the sky, you see the stars move, you write it down. Fire is hot, the sky is blue. It's totally descriptive.
Simple enough. Then, moving into the last few centuries, we hit the second paradigm, which is theoretical science.
Right. This is the era of Newton and Kepler.
Mm.
You use math, laws, generalizations to predict behavior. You have a model, like gravity, and you test the real world against that model.
Got it.
Then, in the late 20th century, we got the third paradigm, computational science.
Mhm.
This is where we started using computers to simulate really complex phenomena.
Like weather patterns or nuclear explosions.
Exactly. Things that were just too difficult to solve with only theory.
And now,
Now, we are in the era of data-intensive scientific discovery, DISD, the fourth paradigm.
okay.
The difference here is subtle, but it's massive. In the previous stages, you started with a hypothesis and looked for data to prove it. In DISD, you start with the data.
You start with the data.
You have
Mhm.
petabytes of information, so much that you can't even see the edges of it, and you let the data tell you what the hypothesis should be.
So it's the difference between looking for a specific book in the library because you think it's there versus having a computer read every single book in the library simultaneously to find connections you didn't even know existed.
That is a completely fair way to put it. But here's the catch,
Yeah.
and this is what the Information Sciences article really drills into.
Yeah.
Our old tools are broken.
Right.
The database technology that ran the world for the last 30 years, SQL, relational databases, it simply cannot handle this shift. So today, we have to talk about the technology that emerged to fix it, which is NoSQL.
Before we get into the nuts and bolts of NoSQL, because I definitely want to understand how that actually works, let's define the scale of the problem. Everyone throws around the term big data, but at what point does data actually become big? Is there a specific number of gigabytes where it crosses the line?
It isn't just a number. The survey defines it using the 3V's framework, which is the industry standard: volume, velocity, and variety. Though some people throw in a fourth V, like value, variability, or virtual.
Volume seems pretty straightforward. It's just the sheer size.
It is, but the scale is honestly hard to visualize. The text uses Walmart as a business case. Think about every time a barcode beeps at a Walmart register anywhere in the world.
Okay.
That happens about 267 million times a day.
267 million transactions daily.
Right. To handle that, plus inventory, plus customer tracking, they had to build a data warehouse with a 4 petabyte capacity.
For context, for everyone listening, a petabyte is roughly a million gigabytes.
Exactly. So we were talking about 4,000 trillion bytes of data. That is volume.
Yeah, that's huge.
But volume alone isn't really the problem. You can just buy more hard drives if you have enough money. The real killer is the second V, velocity. The speed at which data arrives and the speed at which it has to be processed. Take the Large Hadron Collider.
The massive particle accelerator in Europe.
Yeah. When that machine is running, it generates about 60 terabytes of data per day. Or look at the LSST telescope. That captures 30 trillion bytes of image data every single night.
Wow.
This is a fire hose. You cannot just save this to a disk and look at it next week. The infrastructure has to swallow that data stream in real time without choking.
And the third V variety.
This is the messy one, and this is the one that really breaks traditional computers. For decades, data was structured. Think of an Excel sheet.
Rows and columns.
Exactly. Name, date, price. Nice and tidy. But today, data is incredibly messy. It's tweets, it's surveillance video, it's sensor readings from a jet engine, it's audio files. It is totally unstructured.
And traditional databases hate unstructured data.
They despise it. They just cannot handle it. And this brings us to a concept in the article that I found absolutely fascinating. It describes our current hardware situation as being CPU heavy, but I/O poor.
Let's unpack that, because that sounds like the actual root of the bottleneck here.
It is. Think about how computers have evolved. Thanks to Moore's law, our processors, the brains, have gotten exponentially faster. They can do billions of calculations a second.
Right.
But the I/O, the input output, specifically the speed of the hard drive where the data actually lives, has totally lagged behind. The physical rotational speed of hard drive platters hasn't improved much in 20 years.
So the brain is a genius, but it's reading information through a tiny straw.
That's a perfect analogy. The mechanical limitations of spinning hard drives mean we just can't feed data to the processor fast enough to keep it busy. We have all this computing power just idling, waiting for the disk to deliver the information.
And that imbalance is what forced the industry to look for a whole new way to manage data.
Which brings us to the start of the show, NoSQL.
Now, I've heard this term thrown around in tech circles for years. There's this huge misconception that it's an anti-SQL movement, like death to the old ways.
Yeah, that's really common, but no, not at all. The acronym NoSQL actually stands for not only SQL.
Oh, interesting.
Yeah, it's acknowledging that while SQL is great for some things, it's not the only tool we should be using. It avoids selected relational functionality, but it doesn't throw the whole concept away.
So what exactly is the problem with traditional SQL? Why did it crack under the pressure of the data deluge?
Two main reasons: scalability and rigidity. Traditional relational database management systems, RDBMS, are built on schemas.
A schema is like the blueprint, right? You have to
Yeah.
define exactly what your data looks like before you can even store it.
Correct. Imagine a really strict government form. You have exact boxes for first name, last name, and date of birth. If you try to write a paragraph about your day in the date of birth box, the form is rejected. The database yells at you. That rigidity is fantastic for a bank where accuracy and structure are paramount. You don't want messy data in a bank account.
But for Facebook or Google,
It is a nightmare. If you are scraping the web, you have no idea what the next piece of data will look like. It might be a picture, a block of text, or a link. If you have to rewrite your entire database blueprint every single time you encounter a new data type, your system just grinds to a halt.
so NoSQL essentially removes the blueprint.
In a way, yes. NoSQL introduces schema-free design. It completely separates data storage from data management. In a NoSQL system, the storage layer, which is often just a simple key-value store, doesn't care what the data is.
It just holds it.
Right. It just says, give me the object, I will give it a unique key, and I will store it. It focuses entirely on scalability and performance.
It treats the data like a black box. It doesn't need to know if it's a video file or a plain text document.
Precisely. And that allows applications to modify the structure of the data on the fly. You can store a user's name today, and then tomorrow decide to attach their location history and their friend list to that exact same record without breaking the database or rewriting any tables.
Okay, so that handles the variety problem beautifully. What about volume?
This is the other superpower of NoSQL. It is designed to scale horizontally. Traditional SQL scales vertically, meaning if you need more power, you buy a bigger, more expensive server.
But eventually you run out of bigger servers to buy.
Exactly. You hit a physical limit. NoSQL is designed differently. It runs on thousands of cheap commodity servers all working in parallel.
Is this what the big tech giants are actually running their platforms on?
Almost exclusively for their massive user-facing data. The source material highlights Facebook as a prime example. They developed a proprietary database called Cassandra.
Which is now open source, right?
Yes, they released it to the public in 2008. But originally, Facebook hit a massive wall with their inbox search. They had billions of messages growing every second. SQL just couldn't handle the right speed, the velocity.
So they built Cassandra.
Right, to be a distributed NoSQL system that could swallow that massive influx of writes without even blinking.
And now we see Twitter, LinkedIn, Netflix, they all use variations of this to manage their unstructured data. HBase, Cassandra, all of them.
They absolutely have to.
Right.
The fourth paradigm demands it. If you are Netflix, you are tracking every single pause, rewind, and play for millions of users instantly.
Right.
You just can't do that with a traditional spreadsheet model. You mentioned HBase. That's another famous one used in the Hadoop ecosystem, using these things called HRegion servers to manage data.
Okay, so we've solved the storage problem. We have these massive, flexible warehouses, these NoSQL databases that can hold all this stuff.
Right.
But storing a petabyte of data is totally useless if you can't actually read it or learn anything from it.
Exactly.
Mm.
And that is the next massive challenge the paper discusses. Analysis. How do you actually process that much information? Broadly speaking, the industry uses two main ways to do it: batch processing and stream processing.
Let's start with batch processing. This is where Hadoop comes into the conversation. I feel like Hadoop is the ultimate poster child for big data, but very few people outside the engineering world understand how it actually works.
Hadoop is the heavy lifter. It is designed for offline analysis. The core concept driving it is a programming model called MapReduce.
The article used a word count example to explain MapReduce. I thought that was incredibly helpful.
It is the absolute classic example. Imagine you have a library with 1 billion books, and you want to count how many times the word "the" appears in the entire library.
Okay. The old way, the traditional SQL way, would be to have one person start at book 1 and read all the way through to book 1 billion.
Which would take thousands of years. MapReduce completely changes the workflow. The first step is the map phase. You take those billion books and you distribute them to 1,000 different people, or in this case, servers. Each server counts the words in their own small pile of books simultaneously.
So we have parallel processing. Everyone is working at once.
Exactly. Then comes the reduce phase. All those thousands of servers report their individual totals back to a central manager who just integrates the results and sums them up into one final number.
Divide and conquer.
Completely. There's another model mentioned called Dryad that uses data flow graphs, but the concept is similar. That is batch processing. It is incredibly powerful for analyzing massive historical archives. You can process petabytes of data relatively cheaply, but it has a major flaw. It has really high latency.
Meaning it's slow.
Slow in computing terms, yes. It has to read from the disk, do the math, and write the results back to the disk. It might take hours or even days to run a job on a petabyte of data. If you are Google indexing the entire web overnight, that's fine. But what if you're a bank trying to stop credit card fraud?
Right. You can't wait 24 hours to find out the transaction was fake. You need to know during the swipe.
Correct. And that is exactly why we need the second method: stream processing. The need for speed.
This is for the velocity part of the 3 Vs, for things like the Internet of Things or sensors.
Yes. For real-time applications, financial fraud, sensor networks, you cannot wait for a batch job. We use tools like Apache Storm or Kafka. Storm is really interesting because it's essentially the opposite of Hadoop. It's a distributed, real-time computation system.
That is quite a mouthful.
Think of it this way. Hadoop processes a batch of water that is just sitting in a massive tank. Storm processes the water while it is actually flowing through the pipe. It analyzes limitless streaming data in motion. And Kafka, developed by LinkedIn, is a high-throughput messaging system built for that exact kind of real-time activity data.
The article also mentioned something called SQL Stream, which uses no database technology. That sounded almost paradoxical to me. How can you have data analysis with no database?
It's a radical idea, but brilliant. It processes data entirely in memory. It never writes the data to a hard drive before analyzing it. It looks at the data while it's still in the RAM.
Because RAM is thousands of times faster than a spinning hard disk.
Exactly. By skipping the hard drive entirely, skipping that I/O bottleneck we talked about earlier, it can analyze millions of events per second with near zero latency. It sees the pattern before the data even lands on a disk.
That's incredible. So we have the storage figured out with NoSQL, we have the processing with MapReduce and Storm, but there is another bottleneck mentioned in the text, and this one isn't hardware, it's biological.
Ah, yes. The human bottleneck.
Visualization.
Right. Because you can process all the data you want, but if you can't present it in a way that a human brain can actually understand, it's just useless noise. And traditional charts, your standard pie charts or DAR graphs, they completely fail when you have high-dimensional data.
High-dimensional meaning just too many variables to map.
Exactly. If you have 1 billion data points and each point has 50 different attributes: location, time, price, user age, device type, a two-dimensional graph cannot show you those patterns. You need something way more dynamic.
The source points to eBay as a case study here, right?
Yes. eBay uses a visualization tool called Tableau. They deal with billions of items sold and endless search queries. They need to see how search relevance changes based on customer feedback across thousands of different product categories simultaneously.
So they use tools that allow for interactive analysis.
That is the key phrase: interactive. Tools like Google's Dremel or Apache Drill. They allow a user to run ad hoc queries on petabytes of data and get an answer in seconds, rather than waiting hours for a batch job to finish.
Ad hoc meaning I don't have to write a complex program and wait overnight. I can just ask it.
Right. You just ask a question, show me the sales of red shoes in London during the rain. Boom. The answer appears. This interactivity is what actually allows humans to find the needle in the haystack.
This all sounds amazing, but building these massive systems must be incredibly complex. The expert in the source material lays out some specific design principles. If we are truly moving into this fourth paradigm, what are the fundamental rules of the road for building big data systems?
The text highlights three main principles, and the first one is actually the most counterintuitive for people who are used to traditional computing. Bring the analysis to the data.
Explain that, because usually if I want to work on a file, I download the file to my computer.
Right, because your file is small. But imagine the file is 5 petabytes. You can't download that. It would take years just to transfer it over a standard network. The data is simply too heavy to move. So instead of moving the data to your program, you send your program to the data.
You literally upload the code to the server where the data already lives.
Exactly. You execute the computation locally on the node where the data sits. This minimizes network traffic, and it's practically the only way to scale effectively.
Rule number 2.
We touched on this with SQL Stream. In-memory processing. You have to do everything humanly possible to avoid touching the spinning hard disk. To beat that I/O poor bottleneck, processing must happen in RAM. If you go to disk, you lose speed.
And the third principle?
Coordination. When you have a cluster of 5,000 servers all trying to work together on one single problem, it is absolute chaos. What happens if one server dies mid-task? What happens if 2 servers try to write to the exact same file at the exact same millisecond?
You need a traffic cop.
That is literally what systems like Zookeeper do. Zookeeper is a coordination service used by tools like Storm. It manages the zoo of distributed servers, so the main application doesn't have to worry about the chaos.
Looking forward, the survey touches on where this is all going. We've established the current state, NoSQL, MapReduce, in-memory processing. What is on the horizon?
Well, the great enabler of all of this moving forward is cloud computing. The cloud abstracts all the messiness. When you use AWS or Google Cloud, you feel like you're using one giant supercomputer.
But you aren't.
No, you don't see the thousands of messy little virtualized clusters underneath. That virtualization is what makes big data accessible to a random startup and not just massive government agencies.
But the article goes a bit further into the sci-fi realm, too. It mentions granular computing and even biological systems.
Granular computing, or GRC, is a really fascinating theoretical approach. It's about breaking complex information down into different levels of granules, like clusters or groups, to basically reduce the data size and make it manageable. It's a mathematical approach to organizing the chaos.
And biological computing? That sounds wild.
That is the real frontier. We are quickly reaching the physical limits of silicon. So researchers are looking at how nature stores data, using biological models for storage and interaction. I mean, DNA is the most dense storage medium in the universe. If we can harness that, we leapfrog Moore's law entirely.
And quantum computing is the other big wild card mentioned.
Of course, a quantum computer could theoretically solve these massive optimization problems in seconds that would take a classic supercomputer millions of years. But those are still largely theoretical, at least at this scale.
So to recap our mission today, we have moved from the data deluge to the fourth paradigm, DISD. We've abandoned the rigidity of traditional SQL for the schema-free flexibility of NoSQL, and we are tackling analysis with batch processing like MapReduce and real-time streaming tools.
We've basically built an incredible global machine for turning raw, unstructured data into actual knowledge.
But, and this is where the source material throws a massive curveball at the end, the biggest problem facing big data right now isn't the disk speed, it isn't the software, it's us.
The human element, yes. This is a critical takeaway. Despite all this incredible tech, the biggest constraint is people. The technology is advancing way faster than the workforce can adapt.
They cited a McKinsey report in the text that was, frankly, alarming.
It projected that the U.S. alone faces a shortage of 140,000 to 190,000 deep analytical talent positions.
Wow.
And even worse, a shortage of 1.5 million managers who are data savvy enough to actually understand what to do with the analysis.
So we are building these massive mines, Hadoop clusters, NoSQL databases, huge data warehouses filled with gold ore. But we don't have enough miners. We don't have the human expertise to mine it.
Exactly. A NoSQL database is just a tool. It doesn't know which questions to ask. It doesn't know which correlations are meaningful and which are just random coincidences. That requires human intuition paired with technical skill.
So for you listening right now, if you are wondering where the opportunity lies in the future economy, it is right there in that gap.
If you can learn to speak this language, if you can understand why we use NoSQL, or how to design a stream processing architecture,
Yeah.
you become the most valuable resource out there.
The data deluge isn't going away. The question is, are you going to drown in it or are you going to learn to swim?
The tools are built. They're just waiting for someone to pick them up.
Definitely something to chew on. Thanks for diving deep with us today.
Keep questioning everything.
And we'll see you on the next one.